In this problem, we have 10 cans of soda, 5 cola, 4 orange, 1 cherry, and 2 cans are being selected without replacement, and we're asked to find the probability of selecting at least 1 cola. So maybe you get 1 cola or maybe you get 2 colas. So I'm going to go to the next page and give you an idea of how this works. So what are the possibilities? You might get cola the first time and then cola the second time. Right? And this is the first can of cola, this is the second can of cola. Or you might get the first can of cola and the third can of cola. Imagine that they're all numbered 1 through 5. So there are possibilities there. Now you might get cherry number 1. Let me go back. Oh, we only have 1 cherry. Okay, so you might get cherry, or you might get orange number 3. Why not? So there are many possibilities. You might get orange 4 and cola 1. Okay, so here are some of the possibilities. Now there are a lot of different possibilities for this problem, and when you get into choosing even more things, then there would be even more possibilities. So it becomes really cumbersome to list all the possibilities and then find when are you getting at least 1 cola. So when would we be getting at least 1 cola? Well, in the first one we get 2, so that's at least 1. And the second one we would as well. And here we do not have at least 1 cola because none of them are cola. So here, none are cola. And then here we have 1 cola, which means it's at least 1 cola. So we can't just say 3 out of 4 are at least 1 cola because I didn't list all the possibilities. But this gives me an idea of what's going on. So now, when do we not get at least 1 cola? We get the opposite of what we want when we have no cola at all. And that's the key to solving this problem. Because otherwise, I'm going to really have to list out all the different possibilities. So now let's go back. And I say, to calculate the probability of at least 1 cola, oops. All right, I want the probability of at least 1 cola. To calculate the probability of at least 1, you're going to see this more than once. Whenever it says at least 1, we're going to actually do 1 minus the probability of no colas at all. It's a lot easier to find the probability of no colas than at least 1 cola, because we can just find this one individual probability of no cola, and we don't have to find what is the probability that we get exactly 1 cola, exactly 2 colas, and then so on and so forth. So, so this is how we find this. So now, how do I calculate the probability that there are no colas? Well, let's take a look at what we have. We have 5 that are cola, and we have 5 that are not cola. So I add together all the other possibilities other than cola, and in this case that's just orange or cherry. 4 and 1 makes 5, so 5 that are not cola. So when you draw the first can, then you have a 5 out of 10 probability that you get something that's not cola. So now we've done that, and notice that this is without replacement. So when I go to draw the second can, how many do I have? Well, first of all, I have 9 cans because we already took 1 out, and it was either an orange or the 1 cherry. We don't know, and we don't care which one it was. So it was one of those 5 cans. So now there's only 9 cans to draw from, 5 that are cola, 4 that are not cola, and we have a 4 out of 9 probability of getting not cola the second time. So, since none at all is the opposite of at least 1, that's why we're using the 1 minus. This is the complement. So, I do 1 minus, and 5 times 4 is 20, 10 times 9 is 90, and I can simplify that to 1 minus 2/9, and 1 minus 2/9 is 7/9, and that is the final answer to the problem.